All right, all right, all right. Finally, we get to get off this whole notion of derivative is the by definition thing where you have to do the limit as h approaches 0 of fx plus a blah, 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 blah. We finally get to learn some shortcuts. End of the day, if you don't do the practice here, you don't pound out all the different examples that I provide you, it becomes difficult. So this is where practice comes a lot into play. Again, I'm not collecting your homework. I'm never going to do that. Uh, I prefer you just do the problems that you feel comfortable with, making sure you get them done. But this is one section. If they're not complete, you're simply not going to understand or have the capacity to get all the questions right. This is something we'll be practicing a ton of and using a ton of. So objective here, shortcuts of derivatives. Get away from the definition. I could prove all of these by definition, but rather not at the moment. Finding the derivative is the same thing as finding the slope of tangent or your M-tan. I love my M-tan. And it's the same thing as instantaneous rate of change. It's the difference between it's the difference between uh, driving my car and saying I averaged 55 miles an hour than my actual speed at any given moment, which could be anything. Like I could have been driving 90, not that I would ever do that. So derivative, same thing as slope of the tangent, same thing as instantaneous rate of change. Again, abbreviation, mathematicians are lazy. Again, another review on a flashcard that you've already known. If you have a horizontal asymptote, those are going to be critical points. That's where your slope of your tangent will equal 0. It's a location. It is a point or a value of x, depending on how they ask the question. Okay, start off with a couple of rules for shortcuts. If you remember the graph uh, that we're working on, we graphed the function and then we graphed its derivative. We noticed that when we graphed a parabola, an x squared, power of 2, we got a power of 1 function on x. Or if I graphed a cubic, x cubed, I wound up with an x squared as my derivative. Well, that's because that's exactly what the derivative does. It reduces the power by 1 for polynomials. Uh, Non-polynomials are more difficult. We are actually just simply starting with polynomials, and we're going to learn some of these rules through polynomials, even though in some cases we don't have to apply all these rules. But we're going to start with polynomials. Basically, what you have is you have function x to the n. The derivative is simply to place the power in front and take 1 off the power. So n being a constant, you put that constant out in front, and you take 1 off the power. Those are very rudimentary. By the way, n can be any number but 0, um, including fractions. Book says something slightly different and then adds it later. Um, Now I'm going to write a new notation here. If I take the derivative of this junk in here with respect to x, notice how I wrote that and I was reading it at the same time. That's how you read it. So basically this d dx thing, d over dx, d dx means take the derivative of this, whichever's inside that parenthesis, with respect to x. Respect will be important. Trust me. So if I take two functions and I add them or subtract them, basically I can take the derivative of the f function and add or subtract the derivative with respect to x of the g function. It's something that we don't commonly consider a rule after we do some practice. Let's look at example number 2. Number 2 says the function is y equals 1/3 x to the third minus x. Okay, so derivative. The derivative will be 1/3. Coefficients are just hangers. They're like leeches. You can't, I mean, just hang. They're just there. Okay, so I'm just writing the 1/3. All I'm going to do is take the derivative of this guy, just like this guy is. All right. So what I'm going to do is I'm going to take its derivative and put the 3 in front, put the power in front, subtract 1 from the power. Now, you don't have to write that. You know what 3 subtract 1 is. It's 2. Okay? So I did the first term in the polynomial there. Now I'm going to do the second one here. Now be careful. There's actually no power written. But if you just simply just look at this piece alone by itself, it's actually a line. And that slope is -1. So if I'm finding this derivative, I should find the slope to be -1. It's going to make sense. Remember, there is a power of 1 here. Let me get rid of, oh. Okay, this is a pause for my computer, which is now frozen. Come on, puppy dog, you can do it. Okay, there we go. All right, I'm going to take this out, get rid of this. I'll apologize for the technical difficulty. There is a power of 1. Watch what happens when I apply the rule. Subtract, bring the power in front, take 1 off the power. Now, here's what I have. I've got 1/3 times 3 is 1, so it's x squared, minus 1 x to the 0. But what's x to the 0? 1. Anything to the 0 power is 1. So there is my derivative. Again, the derivative is an MTAN. It's an equation to help me find slope at any given point on the original function, as long as you give me an x. I can tell you what the slope is there. Okay, let's erase this one, and let's try another one. Again, you guys are going to see a bunch of different possibilities and scenarios through your problems. Number 4, very basic square function. It's a parabola. Now I know right away, if I remember, I've got a power 2 function. Since it's a power 2 function, I should wind up with a linear function or power of 1 function as my derivative. So let's do this. Let's do this smooth as silk. All right. So put the exponent in front. Take 1 off the exponent. Put the power in front. Remember, there's not 1 written, but it is a 1. X to the 0. But what's x to the 0? Thank you very much, class. Now this is the tricky one right here. There is no variable. There is no variable. Let's just consider this thing right in here for a second. Let's just think graphically for a minute. Let's consider just that by itself. Y equals 1. If I think about that, that's a horizontal line. And we're being asked here to find its slope. What's the slope of a horizontal line? Okay, once again, you guys are wonderful. Thank you so much. It's 0. Okay, if I was to apply the rule, bring this guy over here, and I'm going to apply the rule. It's 1x to, well, I can't write a power. It's got to be a power of 0. What's the first thing you do with a power function? Oh, yes. Again, thank you, class. Pull the 0 in front. But what's 0 times anything? Yeah, 0. So my derivative for this function is 2x plus 1. Again, note, that was the original function is a polynomial. Its derivative is a power of 1 function. Okay, now the product rule. The derivative of a sum or difference is the difference of the derivatives. Okay, we just did that property a number of times here. But the product rule, you can't take the product rule of the parts individually. Okay, it is a special function. Created a lot of drama when they were trying to discover rates for particles of 2 things that basically had 2 functions, and the 2 functions were products together, were multiplied together. So the rule is, if I take the derivative with respect to x, again, I'm reading what I wrote, derivative with respect to x of a product of 2 functions. What I get is the derivative of the first times the second plus the first times the derivative of the second. What I like to say is fig e. Fig plus fgi. Fig e. I have a pause. I have some special friends in the room. I had my little friends visit. I'm so sorry. I didn't know they were here, and it's so awesome. They're so cute. So they're going to sit quietly and watch me teach calculus, and then I'm going to see if they learned anything. By the way, neither one of them's even in kindergarten. Okay, anyway, here we go. All right, example. I'm going to illustrate this example in two ways. First of all, these are simple polynomials. Sorry, I need the function name here. Let's call it f of x is x. Oh, Lord. Got to get my act together. I think the little girls are distracting me here. Okay, so f of x equals x squared plus 1, x cubed plus 1. Okay, clearly I don't, because these are simple polynomials, I really don't have to apply the product rule. None of the problems you experience in this section will be like that. You don't have to apply the product rule. But I want you to do the product rule. Actually, I want you to do it in both methods I show you now. The reason is because it gets you really good at what you would actually do on an AP test with a question like this, and it rehearses you for the next section when I'm required to take L'Hopital or do the product rule. Let me, first of all, in this particular example, I always think algebra first if you can do it. This is a FOIL problem. So f of x is actually x to the fifth plus x cubed plus x squared plus 1. If I view it this way, which you're going to do on an AP test and on the homework, is this derivative is simple. Power in front, take 1 off the power. Power in front, take 1 off the power. Power in front, take 1 off the power. The power on the last one is 0, so this is 0. I'm not even going to write it. Done. Now, there's my slope of my tangent, my instantaneous rate of change, or my derivative, however you want to term it. Now, when you apply the product rule, it's going to be a product of two functions that are not both polynomial. Example of where we're going to need this, and I'm going to put it down here, is a function like e to the x is not polynomial. If I multiply that times a polynomial, I'm now in a position where I cannot simplify like I did in the red, which implies I have to use the product rule. F times G, do the fig E. Okay, I'm not going to start singing. Okay, all right, okay, here we go. Okay, all right, okay, oops, okay, all right, okay. So F times G. To do my derivative of my function, I'm going to do fig plus fig E. I know that's lame. Can't help myself. Okay, so what we're going to do is I'm going to take the derivative of f. If I take the derivative of f, I get 2x plus 0, but I'm not going to write plus 0. If I take a look at g, well, it says right here, it's right here. This is just g right here. So all I'm going to do is write g. G, your hair smells terrific. Ha, ha, ha. Plus, then here it says just write f. Well, there's f. Just copy it. Now I'm required to do a little work. Now I've got to take the derivative of g. Here's g. I'm going to take its derivative. Power in front, take 1 off the power. Okay, so I got that, and that looks sensational. All right, except for now, I did the derivative first. Now I actually have to do some algebra. Okay, where before I did the algebra first, then I did the calculus. So here we go. FOIL, or distribute, sorry, 2x to the fourth plus 2x plus distribute the 3x squared gives me 3x to the fourth plus 3x squared. Combine like terms. Combine. Produces 5x4 plus 3x squared plus 2x. Hello. Same thing. Why? Because both processes work. That's why I want you to do it in class or in your book. I want to actually have you do it in multiple ways. The next rule you need is quotient rule. Okay, quotient rule is a quotient. Very similarly to the product, I'm going to be doing a fig-e approach. It's slightly different though. So a quotient is division, and now the rule is you take the derivative of the first times this to the bottom, subtract. See, that's just like fig VE, only it's subtract instead of add. And then F, G, tick. Or basically you're doing fig, subtract fig E, and then add the G square at the bottom. So it's fig E, subtract, and at the bottom is G square. You're just going to have to know that rule. After a while, it's rudimentary for you. Número 18. Okay, that question says y equals x squared plus 5x subtract 1 over x squared. Now again, these are both polynomials. In this particular case, I probably would say, can I do some algebra? And hell yes, I would. So I'm going to do that in red. I've got division of x squared, but so I can divide each one of them by x squared. Simplify it. So I'm still in algebra class right now. So I get 1 plus 5 over x minus 1 over x squared. Now, this is actually a great illustration. See, now I no longer have a quotient rule. I have what I have here is 3 terms. These are all, I can use the power rule, the first one we learned. The reason is because I want to rewrite this. Instead of writing 5 over x, that's really 5x to the negative 1. Remember, negative powers are reciprocate the term. And then this one is 1x to the negative 2. See how now I have these two things written in power form, so I can now take its derivative? Aha! So the derivative would be 0. Why? Because there's no power there. It's power of 0. Then I go minus 5, bring the power in front, take 1 off the power. Be careful. Minus 1 subtract 1 is clearly negative 2, not 0. Last term, take the negative 2 times the negative 1, bring the power out in front. You get 2. Remember, subtract 1. Negative 2 subtract 1 is negative 3. Obviously, it was originally written in fractional form, so I'm going to go negative 5x over x squared plus 2 over x cubed. So there's the answer. I didn't use the quotient rule. I used algebra first, and then I used the calculus. It allowed me to show you these guys over here where we have the fractional powers. They're kind of tricky. Okay, so now let's just take this and use your quotient rule for it. Okay, if I'm going to use quotient rule, I'm going to have to identify my f over my g so I can do my fig-e. So funny. Y tick equals, okay, not y tick. Say it again. The derivative with respect to x is, I'll keep changing my notation so you get used to all the different notations. Okay, the rule says fig-e, subtract. So derivative of the top, 2x plus 5, subtract 0, times g, minus the top, times the derivative of the bottom. Let me show you what I've got here. I've got fig-e. All that's left is I got to put this over g squared. Well, g is x squared, and I'm squaring it. Okay. Now, I did the calc first here. I did the derivative first. Now I'm going to apply the algebra, which either way you do this is a lot of fun. Okay, so I'm going to go ahead and distribute the x squared. And I'm going to distribute the 2x and the negative at the same time across this term here. So that's going to give me negative 2x cubed minus 10x squared. Wow. Can I rewrite this? I feel like I made a hot mess. All right, let me rewrite this. 2x cubed plus 5x squared minus 2x cubed. I left off, oops, cubed. Oh boy. 2x cubed plus 10x squared minus 2x. Okay, finish the distribution all over x squared square x to the 4th, which equals, adding like terms. Nice. Combine. If I combine those two, it's... Uh-oh. Uh-oh. Oh, there's my mistake. I see it. There's no way because I was going to get the wrong answer. Right here's my mistake. See, that should be a subtract, not a plus. All right, now I feel better. All right, now combine my like terms. 5x squared and negative 10x is negative 5x squared minus the 2x over x to the fourth. See, it still doesn't look like my answer in the red. Okay, so I'm going to do some more algebra. I can separate that into two parts because I'm divided by a single term, which gives me negative 5 over, let's see, reduce that to x squared minus 2 over x cubed. And somehow, like a ding dong, I forgot to distribute my negative. That should have been plus, that should have been plus, that should have been plus, that should have been plus. All right, there you go. Same answer. See, another good reason why you should do it two different ways. Multitasking, we're going to skip that part. We'll probably see plenty of those examples in class, and we'll work those together. That's basically meaning there's a problem with a product rule and a quotient rule, or just multitasking, meaning there's more than one phase. It just makes things real complicated, but we'll work those out in class. So that concludes your first set where you're actually using shortcuts and you don't have to use. The fine and dandy limit as h approaches 0 of f(x) plus h minus f of x all over h, which is the definition of the derivative. Get your work done. I'll have the book assigned and have plenty of questions.